Hey everybody, it's Wednesday, December 16th, and as you can see here in the aim today, our goal for today's video is to discuss orbital motion. And so the main idea that we are going to apply here is that everything we're going to say about orbital motion ties very closely into circular motion, because many objects that are in orbit are moving in circular trajectories. And so what we're going to do here first is talk a little bit about orbital motion and then use some basic concepts to derive an equation. And so, just for some additional information, just for fun, this is a picture of the first object to be launched into orbit. I always think it's interesting to look at, right? We all should know Sputnik, which was launched by the Russians in the space race, was a satellite. And despite the fact that we have a conception of what satellites, or at least modern satellites, look like, this is what Sputnik looked like, this weird little ball with these four little antennae. And so everything that we are going to be talking about today is going to relate to the motion of objects like this, which are in orbit around the Earth. And the main idea that I hope everybody realizes is that objects in a low Earth orbit, which is basically what we always talk about in this course, objects in a low Earth orbit basically move in a circular path. And so because these objects are moving in circular paths, they require a centripetal force, a net force acting on them pointing toward the center of the circle. And so before we get into the equation, I just want to take a minute to talk about what this diagram is showing, because if you've never seen this before, which I'm guessing you haven't, it might be a little difficult to interpret. So basically, the idea is at any point around this circle, like let's just take this point for example, the object has a centripetal force acting on it, which of course is toward the center of the circular path, and the center of the circular path is located right here at the center of the Earth. And so if you remember back to what I said when we first started talking about circular motion, that circular motion is like a battle between the inertia of the object, which wants to carry the object in a straight line, and the force acting on the object toward the center of the circle. So on this diagram here, you have these dashed lines. And what these dashed lines are showing is that if this object, in the absence of an external force, traveled in a straight line, which happens to be tangent to the circular path, it would travel from here, from this black dot, to this point labeled 1 prime. Notice it's just moving in a straight line because that's what Newton's first law says. An object, in the absence of an external force, which is moving at some velocity, will continue in a straight line at that velocity. But of course, the object does not do that. And the object does not do that because it has a force acting on it which is perpendicular to its velocity vector. Notice this straight line, or this straight dotted line here, also happens to be showing you the direction of this thing's velocity vector. And so because this object has a force acting on it which is perpendicular to its velocity vector, it doesn't speed up or slow down, but it does change its direction. And so the path here deviates from that straight line path, and the object, rather than moving in this straight line, follows this curved path here shown by this red line. And that's effectively what's happening at every point. From there, the object at point 1, if there was no force acting on it, would go to 2 prime. But of course, it deviates from that straight line path and would end up at location number 2. And so the basic idea here is that because the object is moving in a circular path, it has a centripetal force acting on it. And the main thing that you need to know, and we are going to write this down after we look at this equation actually, but the main thing that you need to know is whenever you're dealing with an orbital motion problem, you should always be applying the same kind of framework as to how you're going to go ahead and solve that problem. Because the concept is very simple here. This object, because it's moving in a circular path, has a centripetal force acting on it. And the only other question we have to ask is, and the reason we have to ask this question is because centripetal force is not a separate force. It's supplied by other forces. The only question we have to ask here is what force is supplying the centripetal force? And it should be pretty clear to everybody, especially looking at this diagram here with this object located in it, that that centripetal force is gravity. Now, gravity is a perfect force to supply a centripetal force for a situation like this. And the reason why that's true is because whenever you have an object that's orbiting around the Earth, because the force of gravity is always directed toward the center of the Earth, that force also happens to be directed toward the center of the circle. And that's what makes it a centripetal force. And so we'll just write here Fg always toward Earth's center. And then I'll just write in parentheses here, and that's the circle's center. And so that's the basic idea here. And that's the concept you apply. Now, there are going to be basically two kinds of orbital motion questions that I think you're going to see. You're going to see some more of these basic ones, and you're going to see some of these complicated ones. And even if it's like a disgusting, complicated question, which I see from time to time in some of these like upper level physics textbooks that I look at, and I have that panic set in, you know, like we all do when we see a question we don't immediately know how to answer, and you think like, oh my God, what am I supposed to do? You apply the basic concept here. The basic concept is this thing has a centripetal force acting on it, which is supplied by gravity. End of story. And that very concept is the concept that we're going to use to derive an equation for the velocity of an object in orbit. And so I want to be very clear about something. I am showing you how to derive this equation for two reasons. The first reason is the equation that we need will be at the end of this derivation. And so like it's an equation you need to know, and it's not in the reference table. So because it's not in the reference table, it would be a good thing to know how to get it, because then otherwise you have to memorize it. And it actually looks very similar to another equation that we're going to do like in a month. And so it's easy to mix them up. Secondarily, though, and more importantly, they have asked kids on the AP test in the free response section to derive this equation. And so as we prepare for the AP tests and other tests you may be taking in the future, hint, hint, it would be a very good thing to know how to derive this equation. And so let's talk about that now. So as I mentioned, the main concept here is that the centripetal force is being supplied by the force of gravity. And so we take those two things and set them equal to each other. And I'm just going to write a little note here off to the side, which is that Fc is supplied by gravity. And so we take those things and we set them equal to each other. And it should be clear here that the next move is to just write down those equations for those things, because we know the equations for those things. And so the equation for Fc is mv squared over r, and the equation for Fg is g m1 m2 over r squared. And here it's really important to remember that in the gravity equation, like let's just take the example of a satellite orbiting the Earth, like I showed you in that last slide. In the gravity equation, one of these masses is the mass of the Earth, and one of these masses is the mass of the object. Let's just say m2 is the orbiting object's mass. Well, if m2 is the orbiting object's mass, and this mass in the centripetal force equation is always the mass of the object moving in the circle, then that means this is the orbiting object's mass too. And so this m is the orbiting object's mass. And so that means they cancel. And so what we're left over with on the next line then is v squared over r equals g m1 over r squared. Now, it should make sense that the orbiting object's mass cancels, because like as we already know, for an object immersed in a gravitational field, the actual mass of the object doesn't really affect what it does, right? Like if you have a 3 kilogram cannonball or a 30 kilogram cannonball, they're still going to have the same acceleration due to gravity. Like the mass of the object actually doesn't matter. It goes back to like that whole inertia thing. Like, yeah, the object is heavier, so it has a larger force of gravity acting on it, but it also has more inertia. that's the idea here too. And so, according to the centripetal force equation, like if this object had more mass, it would require more force to hold it into the circle. But the force that's holding it into the circle is gravity. And because gravity is proportional to the mass of that object moving in that circle, the very fact that it has a larger mass means there will be a bigger force acting on it to hold it in the circle. And so ultimately they cancel. That's the idea, at least. And then the last move here, and we're basically ready to just get our equation, is if we really wanted to solve this for v squared, we would do that by bringing this up and over here. And that means the r up here would cancel one of those r's down there. And so we'll just cancel it like that. And we'll show here that v is equal to g m. There's no reason to write the 1 anymore because there's only one mass, over r. And then we'll just wrap that up and put it in a box. That's the equation for the velocity of an object in orbit, where, of course, g is our 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. This part's very important, though. M, if you remember, because the orbiting object's mass canceled, m is the mass of the object being orbited, and that's in kilograms. And r, and this part is super important, r, as always for these equations, is the distance between the centers of the objects. Now, that's very important, and I'll just put over here, I guess, that v is the orbital velocity measured in meters per second, where, of course, also the r is measured in meters. It's very important that you recognize that r is the distance between the centers, because when an object orbits the Earth, it never orbits it like on the surface of the Earth. You have the radius of the planet, and then the object is going to be orbiting around in a circle that's like some height above the surface of the planet. And so the idea here is pretty simple, I think. It's that when you want to find the distance from the center, and you know the radius of the planet and the height above the surface of the planet, then the r in that equation, and I'll just write here like radius of planet, rp, r is going to be equal to rh plus rp. You're actually going to do that basically every time you solve a problem, because they are not going to tell you how far the object is from the center of the planet. They are going to say it's orbiting, like 100 miles above the surface of the Earth. And so you'll need to add the radius of the planet to the height of the orbit. So I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll take a look at some notes before we solve a problem. Okay, now, as I mentioned, they've asked you to derive this on an AP test before. And orbital motion questions are totally fair game as far as the AP test is concerned. So very large note here, to derive the orbital velocity, or anything else related to orbits really, you just set the centripetal force equation equal to Newton's universal law of gravitation, and you solve it for v. Take a second to pause this video here and write that down, and when you hit play, we'll really take a moment to analyze this equation. So, before we move on and solve a problem, I just want to write a couple of notes here about the structure of this equation, because I think there are some things about this equation that are really important for everybody to understand. The first thing, and we already mentioned this, but it's good to write down, is that this equation is not dependent on the mass of the object in orbit. Not dependent on the mass of the object in orbit, but only on the planet being orbited. Remember, it goes back to that whole inertia thing. Additionally, as you can see here, the orbital velocity is directly proportional to the square root of the mass of the planet. And so at a given radius, if all of a sudden the mass of a planet got larger, like obviously that's not going to happen, but just for an intellectual exercise, at a given radius, if the planet's mass is larger, essentially what this equation is saying here is that the object's speed must be larger to avoid being pulled into the planet's surface. Keep in mind, the v from this equation comes from that centripetal force equation. And so essentially what that speed, v, is telling us is this is the speed the object needs to be going in order for it to be moving fast enough to prevent from being sucked into the center of the planet by the gravitational force. That's the idea. Essentially, what we're saying is this object has a tendency to move in a straight line at such a large speed that gravity doesn't actually pull it in, and it doesn't fly away in a straight line forever, but it stays in that delicate balance and moves around in a circle. And the last thing that we'll say here is that the orbital velocity is, let's just get rid of that here. Let's just say the orbital velocity is directly proportional to 1 over the square root of r. And what that means is that if the orbital radius was decreased, meaning the thing is closer now, the velocity the satellite would have to travel would have to be faster, because the gravitational force acting on the satellite is going to be larger when it's closer to the Earth. And so the idea is, like, if we're talking about a satellite orbiting this far away from the Earth, and then we move it in and put it here, the r is decreasing. And so what this equation says is that the speed is going to have to increase in order for this thing to prevent itself from being sucked into the surface of the planet. This thing is going to have to go faster so that it has enough speed such that its inertia will prevent it from being pulled into the surface and crashing, essentially. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at a problem. Okay, let's take a look at a problem. So this problem here is in the gravity packet. It's on page 5, number 46. It says, calculate the speed of a satellite moving in a stable circular orbit about the Earth at a height of 4,800 kilometers. So again, it's very important for everybody to realize here, when they tell you the height, what they are telling you is there's the surface of the Earth. This object is 4,800 kilometers above the surface of the Earth. And so when you're going to write down your list of knowns here, you're going to write it down like this. So we'll say here first, we got to look at this chart because we need information about the object being orbited. We know here the mass of the Earth, as you can see here in this chart, is 5.98 times 10 to the 24 kilograms. So the mass of the Earth is 5.98 times 10 to the 24 kilograms. We also know the height of the orbit is that number they told us in the problem, 4,800 kilometers. Now, you're going to have a big problem if you start mixing up your units. And obviously, we have to keep all our units straight in terms of having them all be in meters, just to make the units in the actual equation work out. And so we want to make sure that we write this. And so this in meters is going to be 4.8 times 10 to the 6 meters. Now notice this would be 4.8 times 10 to the 3 kilometers, but then you have another 3 for the kilometer, so it makes it 10 to the 6. And so we have the radius of the Earth here, which I'll just write RE, is 6.38 times 10 to the 6 meters. Now, I just want to go back to this chart for a second, because I know this particular chart says 6.37, but like basically every other chart, including the other one that's on this planetary data reference table, says 6.38, and that's the number I always have in my head, so that's just the one I'm going to use. At the end of the day, you should realize that it doesn't really matter that much. And here, of course, big G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Notice we can also write that as meters cubed per kilogram second squared. I'm actually going to plug that in because I just want to show you how the units end up working out here. And then we're looking for the speed. The speed is square root of gm over r. And so we're going to have the square root of g, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. The mass of the Earth, 5.98 times 10 to the 24 kilograms. And then we divide that by, remember, the sum of those two distances there. So we have 4.80, or 4.8 times 10 to the 6 meters, plus 6.38 times 10 to the 6 meters. And when you plug that into your calculator and you do all that math, you get 5,973 meters per second. And because all of these numbers, at least in that reference table, are given to 3 sig figs, we'll call it 5,970 meters per second. And so what that means, I just want to be very clear for a second about what that means. What that means is it would have to have this speed to maintain that orbit at that radius. Take a second to pause this video here and write that down if you haven't already. And when you hit play, we'll take a look at one last question regarding orbital velocity. All right, before we wrap up this piece about orbital velocity, let's just take one quick look at a question before we move on. And this question says, how can we describe the effect of the satellite hitting a piece of space junk that slows it down? I want you to take a second to pause this video here, and I want you to think about how we could describe the effect of the satellite hitting a piece of space junk that slows it down. And when you think you've come up with an answer, hit play, and we'll go over it. Okay. Now, this question, I think, is easier than it looks. And that's why I want to take a moment to talk about it. Because the equation that we're dealing with here, this orbital velocity equation, is actually pretty misleading, I think. Because if you look at this equation, you'll get the idea that the orbital velocity is inversely proportional to the square root of the radius, which is true to some degree. For sure, it's true. But it gives you a false interpretation if you think of a question like this. Because you could pretty easily look at that equation and think, well, if the speed of the satellite is decreasing now because it hit this piece of space junk and it slowed down, then the speed here is going to get smaller. And if the speed is inversely proportional to r, then that means r has to get bigger. And so if this is the planet, instead of the satellite orbiting with this orbital radius, it's actually just going to move out to a larger orbit. That's wrong, though. And to understand why that's wrong, we have to take a look at this piece by piece. And I'd like you to write this down because this is very important. If the satellite hit a piece of space junk, the first thing we can say is that the velocity of the satellite will decrease, in this scenario at least, which means the orbital radius must change. It has to change. Now, it's very important, I think, to answer this question, to make sure that you are interpreting what this equation is telling you properly. This equation is telling you, in order to maintain an orbit at a specific orbital radius, the speed must have a certain value. When you plug an r into this equation, v equals the square root of gm over r, what that equation tells you is at that radius, for a planet of whatever mass it happens to be, this is the speed the object has to have. The important thing to realize, though, is that the speed, because of the crashing into the space junk, is now less than that. And so the point is This means the object could only maintain an orbit at its new slower speed at a larger orbital radius. This is what we were talking about before. Essentially, what this equation also kind of tells you is that if the object was here and is now slowed down, well, that new speed that it's at is only going to work out here at this new orbital radius. There's a problem with that, though. The problem is that since the object isn't just going to magically move in the opposite direction of the net force, it's actually going to fall in to the planet. The idea is it gets slowed down here. It can't be here going that slow. It can only be here going that slow. And so basically, because it can't be here going that slow, the only way it could possibly be going that speed is to be out here. But since moving out there would require the object to move in the exact opposite direction of the net force, it's not going to do that. The net force is just going to take over and the object is going to crash into the planet. It's kind of a hard thing to understand, but if you think carefully about it, it'll start to make sense. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So, for the last part of this video here, we are actually going to go back to something we've already talked about. Because we are talking about orbital motion, we're going to go back and talk about Kepler's laws. And we're going to do this very quickly, but as I mentioned, Kepler's laws fit nicely into gravity and circular motion. And since now we're talking about circular motion, we might as well just circle back to that, get it, really quickly. And so the first thing we'll say here is in this course, we'll make the basic assumption that all orbital motion is circular motion. It's an approximation. Now, I'm sure some of you may be thinking, well, isn't that kind of weird? Because you said we were going back and talking about Kepler's laws, and don't Kepler's laws say the orbit of any planet is an ellipse? I guess, yeah. But it's important to remember that a circle is just a special case of an ellipse with a special value for the eccentricity. And the significance of this approximation is that it'll allow us to write an equation for the velocity of an object moving in a circle. Now, this, of course, is not the equation that we just came up with, but the good old-fashioned V equals d over t. And now we need to ask ourselves a question. When an object is moving in a circular path and it goes around that circle once, what is the distance that object travels? The answer is the distance it travels is the circumference of the circle. And it travels the circumference of that circle in the amount of time it takes to go around once, to make one complete trip. And the amount of time for an object to complete one full orbit, if you remember back to Kepler's law, is called the period. And so the equation here for the velocity of an object in orbit would be 2 pi r over t, where r is the radius of the circle, and t is the orbital period. And that's going to be measured in seconds. So we get meters per second. And so what we can say about this here, of course, is just to summarize that since the distance an object travels when it completes one full orbit is the circumference of the circle, and the time it takes for a complete orbit is defined as the period, the velocity can be written as the ratio of the circumference to the period. Take a second to pause this video here and write that down. And when you hit play, we'll go ahead and derive Kepler's third law. So, You can write this under the heading Derivation of Kepler's laws using Newton's universal law of gravitation. So the first thing we're going to do here when we're going to derive this equation should be obvious to everybody based on what we've already said in this video here. We are going to set the equation for centripetal force equal to the force of gravity. And that's because the object is moving in a circular path where gravity is supplying the centripetal force. And so just like we did for the orbital velocity equation, we're going to take mv squared over r, and we're going to set it equal to g m1 m2 over r squared. And as we did before, we have the mass of the object that's in orbit canceling, leaving behind only the mass of the object being orbited. So it's very important to remember m here is the mass of the object being orbited. And so that leaves us with v squared over r equals gm over r squared. And what we can do here now is we can recognize the fact that we just discussed, which is that for an object experiencing circular motion, we can say that the velocity is a ratio of the circumference to the period, 2 pi r over t. And so that means we can sub in here for the velocity 2 pi r over t, and then put that over r like this equation says. And then we have that equal to still gm over r squared. And so that leaves us with a rather disgusting expression, 4, because we got to square this whole thing, 4 pi squared r squared over t squared, that just pops down to the denominator, times r equals g m over r squared. Now, of course, I've run out of room, so I'm just going to go ahead and recopy that on the next slide. So we have 4 pi squared r squared over r t squared equals g m over r squared. And so the first thing to notice is that this r cancels one of those r's, and we can rearrange this to solve for really anything we want. But let's go ahead and solve for the period squared, t squared. We're going to do that by bringing the t squared up and over, and that means we're going to have to bring this gm down. And so we're going to have 4 pi squared r, put the gm in the bottom, and we're going to have to bring this r squared up top, and there's already an r up there, so we're going to have r squared times r is r cubed. R cubed. Does that look familiar? I hope so. Because if you remember, what we said Kepler's third law said is that the ratio of t squared to r cubed is constant. And the reason why is because if we took this equation in the box now and we divided both sides by r cubed, you would get t squared over r cubed equals 4 pi squared over g times the mass of the object being orbited, and all of those things are constant. And so we'll say here, since everything in the equation is constant, or rather everything in the parentheses is constant, t squared over r cubed is constant. And that's Kepler's third law. Now, when we were first discussing this, we also said there's a second version of Kepler's third law that you can use to calculate the mass of any object being orbited. And notice, if we just rearrange this equation to solve for m, basically in this line, all we have to do is switch the location of the m and the t squared. So we get 4 pi squared r cubed over gt squared. So we get 4 pi squared r cubed over gt squared. And that's it. If you know the orbital period and radius of an object in orbit, you can calculate the mass of the object being orbited. And that's pretty cool. Now, before we go ahead and solve a problem, there are a few quick notes that I think we should write down about this. So I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll write down 2 more quick notes, and then we'll solve one last problem here very quickly before we go. 2 quick notes here before we solve a problem. First note, despite the fact that this was originally written to find the mass of the sun, if we use the period and mean distance for any orbiting object, we can use this equation to find the mass of the object around which it's orbiting. So if we realize that any planet has a moon, we could just look at that planet and then figure out what the mass of that object is. And additionally, and this is an important note here too, to make the units work out, the period must be in seconds and the distance must be in meters. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at a problem. So let's take a look at one last problem here very quickly before we go. This problem here is in the gravity packet. It's on page 6, number 60. It says to determine the mass of the Earth from the known period and distance of the moon. And do you know the period and distance of the moon? Because I don't. But of course, we can use our trusty chart here. And it says here for the Earth's moon, the orbital radius is 3.85 times 10 to the 8 meters. And the orbital period is 27.3 days. So that's annoying. The moon is an annoying one because they only give it in these charts in days because that's like the lunar cycle. And so we'll have to convert it to seconds. It's no big deal. It's just a little annoying. And then, of course, we're going to use that to find the mass of the Earth. And, of course, we could squeeze big G in there. 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. So our first move here is we've got to find 27.3 days in seconds. And so we're going to put 1 day in the bottom. And we could say that's equal to 24 hours or whatever we'd like, but that's why I always said it's a good thing to remember that there are 86,400 seconds in a day. And so all you have to do here is take 27.3 and multiply it by 86,400. And when you do that, you get 2,358,720 seconds. Or, because all the other numbers are given to 3 sig figs, and if we want to do this unit conversion, we want to preserve the number of sig figs, we'll say that's equal to 2.36 times 10 to the 6 seconds. So I'll squeeze that in here, 2.36 times 10 to the 6 seconds. And now we're ready to go. According to that equation we just derived, the mass of the moon is, the mass of the Earth is going to be 4 pi squared r cubed over g times the period squared. And so we get 4 pi squared r cubed, which is 3.85 times 10 to the 8 meters. We're going to cube that whole thing. And then we're going to divide that by the product of g, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, times t squared. And we said our period here is 2.36 times 10 to the 6 seconds. We're going to square that. And when you do all that math and you plug in all those numbers, you get, for the mass of the Earth, 6.06 times 10 to the 24 kilograms. Now, it's important to realize that's not the mass of the Earth we used before, because the mass of the Earth we used before was 5.98 times 10 to the 24 kilograms. But it's also important to realize these numbers are not as precise as we know them. It's important to realize 3.85 times 10 to the 8 is not a very precise number. It's only 385 million. Notice no other information in any of these places, let alone in decimal places. And 27.3 days is also not that precise. Because essentially, it's important to realize what that is. We're saying, it's between 27 and 28 days. Let's just call it 27.3. It's about a third. So it's important to realize it's not to say that these equations are broken just because the number didn't come exactly out to 5.98 times 10 to the 24 kilograms. It's because we're using numbers that are not as precise as they could be. However, additionally, it's also important to say this equation assumes the moon moves in a perfect circle. And we know that it does not. It moves in a slightly elliptical path. And so Kepler's laws are also a little fishy for that reason as well. Additionally, we can also say that Kepler's laws were written under the assumption that each planet orbiting the sun was only affected by the gravity due to the sun, or in other words, was only affected by the gravity of the thing it was orbiting. So like the moon would only be affected by the Earth's gravity. It's not exactly true, because of course the moon is affected from the gravity from the sun as well. And so Kepler's laws are good, but it's important to realize their limitations. And with that, that's it for today. Have a good one, everybody.